So here's Glenn.
Wiggle it like you did.
Wiggle it just a little bit. Whoa! Woo!
All right, so that was a very obnoxious example of our next topic in this course. So our next topic is chapter 5, weathering, erosion, and sedimentary rocks. So what you just saw took place in Goblin State Park in Utah, and you just saw some person do about 10,000 years of natural erosion in one day, which is awful. That person was fined by the Park Service and is also no longer allowed to lead Boy Scouts because he destroyed part of the natural environment in the state park. And that's an example of what's called biological weathering, the breakdown of rock by organisms. And weathering creates sediment. That sediment can be transported, which is a process called erosion, and then it can become some of the building blocks of sedimentary rocks. So that kind of explains how all of these topics are connected in chapter 5. So let's start out with talking about the surface of the earth. I took this picture on a geology trip outside of Denver, Colorado, a few years ago. I was at a conference for the Geological Society of America, which is what all the cool kids do every October or so. And there had just been a bunch of flooding and landslides in and around the Denver area as a result of a lot of precipitation. It was called the Front Range floods. You'll see more pictures of that in the coming chapters. And so this is an example of the creation of sediment right here. And so very often in areas where you see bedrock exposed right at the surface, which is called an outcrop, you will also see signs like this, like rocks for the next 2 miles, which I'm going to be honest, even as a geologist, I don't really know what you're supposed to do. Just drive fast and look for landslides, I guess. But either way, this demonstrates what happens when rocks weather. Weathering is the physical and the chemical breakdown of rock. We will talk about some of the different processes that occur in physical weathering and some of those that occur in chemical weathering. Once rocks are weathered, a whole bunch of different interesting things can happen to them. But basically, rocks weather because they're exposed to new environmental conditions. A lot of times, rocks will form deep in the Earth's crust, right? Like when we think about intrusive igneous rocks, they'll cool at temperatures that are hundreds, if not over 1,000 degrees. And so the surface of the Earth is certainly nothing like that. So what happens is that these rocks are unstable. The minerals in them become unstable under these new conditions at the surface of the Earth. Lots of, like if you think about metamorphic rocks, most of them form within the Earth under extremely high temperatures and pressures, which again are nothing like the surface of the Earth. So those minerals are only stable in the conditions that they form in. What happens is when they get exposed at the surface, those minerals start to break down, and the more unlike their initial conditions, the faster they will break down. Once rocks begin to break down, they can then be moved, and they're moved by the process called erosion, where rocks are moved from one location to another by wind, water, and ice under the influence of gravity. Once that happens, that can result in events like we see here, mass wasting. This is a very small rock slide, but rock slides, we'll learn in a few chapters, can be massive and very destructive. Sometimes the sediment then will accumulate either as soil, which is obviously super important to people who have a need to eat to stay alive, or they can become part of sedimentary rocks. They can then become compacted and compressed and cemented together as the primary components of sedimentary rocks. So this is where sedimentary rocks really start. So not all rocks weather the same. And if you think about it, you can probably come up with some reasons why. What do you think? What do you think can control whether things break down faster? Well, if you just think about what I just said about environmental conditions being very dissimilar on the surface of the Earth, we know that different minerals will form at different temperatures and pressures. So the composition of rocks 100% will impact how quickly they weather. So minerals tend to weather in the same order that they crystallize. And that makes sense if you think about it. If you think about a mineral like olivine, that green, grainy, sort of sandy looking mineral, it is it forms at very high temperatures. You probably remember from our conversation about fractional crystallization. When minerals cool in a magma chamber and start to settle to the bottom, olivine will form at about like 1600 degrees Celsius. So the surface of the earth is nothing like that. So olivine is really unhappy at the surface of the earth. So this is kind of a complicated chart. I'm going to make it a little bit simpler, but I want you to take a minute, and this is what the chart looks like in a lot of textbooks. I'm going to get rid of some of the words you probably recognize, and some of the words are really new to you. So I'm going to get rid of some of them. Basically, these are mineral families. I'm going to give you the examples of the minerals that you saw in lab to help make a little bit more sense. So let's start all the way over here on the left first. Basically, the left shows you that the minerals at the top of this chart cooled at highest temperatures. They went from a liquid to a solid at very high temperatures. And here we see olivine at the very top at about 1600 degrees Celsius. And then as you move down the chart, the temperatures get cooler. These are the last minerals to crystallize, and they cool at the coolest temperatures at about 600 degrees Celsius. So there's about 1,000 degree difference between minerals that form at the top of this chart and mineral form at the bottom. And here you see our old friend quartz, which we talk about honestly all semester long. This chart is called Bowen's reaction series, and it's named after Nicholas Bowen, who was a geochemist who figured out that minerals do cool in a really predictable order. And so we can use that not only to understand magma processes, but we can also use that to understand weathering processes, because these minerals that cool here at the top of Bowen's reaction series in general, these minerals are minerals that form at high temperatures. And so they form in conditions super unlike the surface of the earth. So they are the least resistant to weathering. They're going to break down the fastest. And minerals that cool at the lowest temperatures, like orthoclase, muscovite, and quartz, those are going to be the most resistant to weathering because that's the most similar to the surface of the earth. So Bowen did a whole bunch of work in and around the area around New York City, along an area called the Palisades, which is a famous spot in New York and New Jersey. It's a big igneous intrusion. It's called a sill, which you learned about last chapter, and it was mined heavily for construction materials because it's relatively resistant to weathering. But that's where Bowen created his reaction series that is super important to geology. So let's think about what these minerals look like at the top of Bowen's reaction series. We have olivine, augite, hornblende, and biotite. So these are all relatively dark colored minerals. So your mafic minerals, which are your darker colored minerals because they're rich in magnesium and iron. These minerals form at the highest temperatures. And so they're the least stable on the surface of the earth. And remember, plagioclase is a mineral that when you saw it was mostly white, but it can actually be all the way to really dark gray. If you had plagioclase that had a lot more calcium in it, it would be dark gray in color. I know we often think of calcium as white because of milk, but calcium is a metal. And so the more calcium you have, actually the darker the plagioclase will be. And so plagioclase is part of a mineral family called feldspars, and there's a dark variety of it. You saw a pretty light variety of it. Orthoclase is often called plagioclase feldspar because it's also very similar. It's just the potassium in it makes it kind of a pinkish salmony color. So then if we think about the minerals at the bottom of Bowen's reaction series, orthoclase, muscovite, and quartz, these are the lightest colored minerals. And so therefore, these are your most felsic minerals. So your felsic minerals form at the coolest temperatures, which is true if you remember some of the characteristics of felsic or granitic magma is that they generally have a really high silica content and they form at cooler temperatures, which leads to them having a higher viscosity. So your lighter colored minerals, because they form at cooler temperatures, are more resistant to weathering because those cooler temperatures are more similar to the surface of the earth. And so this is a picture I took in the field on a field trip one day. This is a metamorphic rock, and there are bands of light colored minerals, which is this whitish gray color. And then there are bands here of darker colored minerals. And this is a rock hammer for scale. This is about 18 inches in length. one of the things I want to point out is that look at the dark colored minerals. They weathered right out. I'm not sure that you can totally tell from this picture, but you could stick your finger right in this little divot in the rock, and it's because all of these dark mafic minerals, probably augite and hornblende, weathered out way faster because they were way less resistant to weathering than the more felsic minerals of plagioclase, orthoclase, and quartz that you see here. So, weathering rates are controlled in part by what a rock is made up of. And you can see that actually in graveyards. If you ever want people to think you're a little strange, you can walk around and take some pictures of headstones. So both of these headstones were installed in about the same time, but you can see that they look tremendously different, right? They've weathered tremendously differently. So here you have the headstone on the left, which is very well preserved, and the headstone on the right that is much less well preserved. It's much harder to read, and that's because these headstones are made of different materials. So the headstone on the left is actually made of granite. Granite, as you recall, is full of really felsic minerals, which are generally very resistant to weathering. We just saw that on the last slide. And on the gravestone on the right is composed of a rock that we're going to learn about this chapter called limestone. And the minerals in granite and limestone are very different, so granite and limestone weather very differently. So as I just mentioned, granite is full of felsic minerals like orthoclase, plagioclase, muscovite, and quartz, while limestone is primarily composed of the mineral calcite. So what do you remember about calcite from our last chapter on minerals? So do you remember? It has a funny little quirk. It reacts to acid. It reacts vigorously to acid, and it bubbles immediately. So what happens is that precipitation is not obviously very acidic because it would burn your flesh, but precipitation is slightly acidic. So what that means is that when it rains, calcite or limestone, which is containing the calcite, will begin to weather, and it will begin to chemically react, and it will begin to lose some of the definition that you see. So if you're looking for a discount gravestone, limestone and marble are your best deals, while granite is certainly more expensive, and that's because it breaks down slower. Yep, that's right. Geo 101 giving you lifelong advice. Here's another picture. Oh, these were taken in the Mammoth Cave Cemetery and Mammoth Cave National Park in Kentucky. The Cutliff family had much more money. So these are then the family I'm going to show you in just a second. This is a metamorphic variety of granite. When granite gets metamorphosed, and you can see that it's metamorphosed because you can see all the light and dark bands here. When granite gets metamorphosed, it turns into a rock called gneiss. And that's what you can see this headstone is composed of. So it's still felsic minerals, still super resistant to weathering. So Mammoth Caves is in an area with a lot of limestone bedrock. So this is one of the creepiest graves I've ever seen. This is made right from Kentucky limestone, right from the earth. And this is a hand carved gravestone. And this one also, again, this was installed in like the 1920s. You can already see that this is already a little bit harder to see. It's starting to break down so much that there is lichen and plants that are beginning to grow on the top of it. And these are fake flowers. But nevertheless, you can see the difference in weathering. Again, both of these headstones installed about the same time. Okay, so the next thing that can greatly impact whether or not rocks weather quickly is the presence of fractures in a rock. And that's because when there are fractures in a rock, water will rush into those fractures, and the water is incredibly important in all chemical weathering processes. So this is a picture from Arches National Park. And these were my children a long time ago in front of the Arches National Park sign. And there's no arches in this picture, but we see the remains of the arches here in what's called balancing rock that used to be connected to this rock over here. So there was a arch that collapsed. So Arches National Park is really cool. So this is an aerial view of it from Google Earth, and I'll show you the arches in just a second. But what my eye is drawn to is a couple things. So you have the red and white color, but then you also have like these deep fractures that you can see in the rock. And that's because there was an event where part of the ground below Arches National Park actually collapsed. And when it collapsed, it created all these fractures in the surface of the earth. And there you see an arch, and you see one of my daughters rushing towards the arch. This is actually called double arch. You can see there's two here, one in the background and then one in the foreground there. This is in Utah. Lots of the pictures from today are from Utah, and that's because Utah has really well preserved weathering features because it has a relatively dry climate. So this diagram is going to show you the progression of the creation of arches, and what you saw from the aerial perspective were these fractures. What's cool about Arches National Park and what makes a big difference in the weathering of it is that there's relatively resistant sandstone here where a lot of the fractures are, and then the sandstone overlies a softer shale. You can actually see the contact here between the sandstone and the softer shale, and the shale is going to erode away faster than the sandstone. That's going to be part of the contributing factors to the creation of these arches. So the water will, when it precipitates in Utah, will rush down through these fractures and deepen the fractures and widen them and round them a bit. And they'll create these long, narrow areas called fins often. And there's the sandstone below the fins, for the most part, stays intact, but the shale, the soft shale underneath, erodes away. And so you start to have a little bit of that sandstone collapse down, and that fin will get thinned from both sides. Eventually, the fin will become so thin that it opens up so that it creates an arch, so you can walk from one side of the fin to the other. And there's more and more collapse over a long period of time until you get incredibly thin arches that can sometimes collapse. And that's what we see in Arches National Park. We see right now a steady state of the creation of arches. So arches are being created in Arches National Park at approximately the same rate as they're being destroyed by gravity and weathering. So I think something crazy like 67% of known arches exist in Arches National Park. It is just awesome, and it is outside of a very cool little town called Moab in Utah, that is known for lots of different like outdoor sports, including like dirt bike racing and stuff like that. All right. Oh, so here is the most famous arch in Arches National Park. It is called Delicate Arch, and I wanted to show it's on the Utah license plate, but I wanted to show it here with people for scale, so you get an idea of really how tall Delicate Arch is. I'm pretty sure it is something like 80 feet tall. It is pretty awesome. Okay. So another feature or another characteristic that is going to impact how quickly things weather is the climate of an area. And so here we have two very different extremes, right? On the left, you have a climate that is much wetter, just generally wetter. And it's more of like a tropical rainforest type environment. And on the right, you have another extreme. So this is also outside of Moab, Utah. This is Canyonlands National Park, and you can see one of the canyons sort of here off to the right. It is an incredibly dry environment, and weathering is going to occur much faster in the tropical environment than it does in the dry environment. Because chemical reactions occur most quickly in hot, wet climates, weathering will also then occur most quickly in hot, wet climates. If you've ever heard of slash and burn techniques for farming in tropical rainforests, that occurs because there's so much precipitation that any nutrients that are in the soil get kind of leached out with the precipitation, and the soil becomes very nutrient poor. So what people will do is that they will slash the trees, they'll cut the trees down, and then they'll burn them. The nutrients that are stored inside the trees will then fertilize the soil, but unfortunately, because they're in such a wet climate, that soil will be largely barren again in about 7 years or so, depending on how much the soil is used. So it's a short-term solution to a much larger problem. Agriculture also isn't great here in Utah, as you might imagine. There's very thin soil, and a lot of places there's no soil at all. But weathering will occur much slower here. Even though it's very warm, there is very little moisture, and so that all of the chemical weathering processes will take quite a bit of time. So the last factor impacting weather rates that we're going to discuss is surface area of rocks. So this picture is taken in Hickory Run State Park in Pennsylvania, and I have a fun random story about this. So one of my friends, Irene, who's a geologist in Long Island, was having a bachelorette party and thought that the best way to celebrate that would be to go whitewater rafting, which is odd, but nevertheless, we went and camped in Hickory Run State Park and went whitewater rafting. And about a month earlier, one of my students had asked me if I had heard of the boulder field in Pennsylvania. And I had not. And I said, well, what is it? And he was like, it's just a giant field of boulders. And I was like, that's weird. And then there I was driving through Hickory Run State Park, and I saw a handwritten sign nailed to a tree that said Boulder Field to the right. So I followed the signs, and here I was. I ended up at the Boulder Field of Hickory Run State Park, and it is extensive. It's about a mile, maybe 2 or 3 miles long, and about a half a mile wide. And I want you to know that I cropped out over here on the left-hand side. There was 2 old people making out, and I mean old people, and that was weird. But I really needed to take pictures of this really awesome boulder field. The boulder field, this is a picture from the sign that was there. It explains sort of how this boulder field formed, that there were fractures. And we already learned that the presence of fractures will help to increase weathering rates. What happens is as the rocks begin to break down, the amount of surface area that is exposed to the air increases. And that greatly, the higher the surface area, the faster the weathering in general. And if you've ever made mashed potatoes, you should know this, right? So when you mash potatoes, first thing you do is you peel the potatoes and boil the water, right? And then you cut up the potatoes, and you cut it up because the more of the potato that's in contact with the boiling water, the faster that potato will cook. And that's the same concept here of surface area, is the more that is exposed to the surface, then the quicker the weathering will occur. So here you have, this is kind of just a generic diagram of a chunk of rock. I'm going to show you 3 diagrams, and they all are the same volume of rock, but the surface area is going to increase as they get smaller and broken into smaller and smaller chunks. So if you have a rock that's 2 feet by 2 feet, and you were supposed to figure out how much of this rock is exposed along the 6 faces of this cube, you would take the 4, which is the area of the rock, the length times its width is 2 times 2, which is 4, times 6 sides, and you end up with 24 square feet in this case, if we made the units feet on this rock. So a rock that is 2 feet by 2 feet has a surface area of 24 square feet if it is a cube. If you take that same 2 foot by 2 foot rock and you broke it into 8 pieces, like you see here, the surface area doubles. It goes on so you still have, because you have 8 cubes, basically, it increases dramatically. And then the smaller the cubes you break down into, the larger the surface area. And then the larger the surface area, that means that water can react with all 6 sides of all 64 of these cubes. So those are the 4 big factors that influence the the velocity of weathering, really, the rate of weathering. What we're going to talk about next are the 2 main types of weathering and then what those entail. And there's not a ton of text on these slides, so I would encourage you to kind of take notes as you go along, because I think that this particular chapter is sort of best illustrated with pictures and just sort of thinking through how things work. So we're going to talk about 2 types of weathering. We're going to talk about mechanical weathering, and then we'll talk about chemical weathering. Mechanical weathering is the physical breakdown of rock into smaller pieces. So if you were to take a rock, or if you take a piece of paper and you rip it up and you have a whole bunch of little pieces of paper, you have just mechanically weathered that paper. There are different ways that rocks can end up being broken down over time, and one of those is through a process called frost wedging. So if you live in the northeast of the United States, you are familiar with this idea, which is that when it gets cold, water can percolate down into cracks, and then that water can freeze. When it freezes, water expands, and that will widen and lengthen cracks. And that's what you see happening here. Eventually, cracks can widen and lengthen to the point where chunks of rock actually fall off. And this is called frost wedging. And again, it occurs because of the freezing and thawing of water in fractures in the rock. So this is how potholes are created in roads, especially in the Northeast. When you think about the number of freezing and thawing cycles we have over a winter on roads, and then you drive into said pothole and then need an alignment or hopefully not a new tire to your car. So that is the process that creates the features that we see here at Bryce Canyon National Park in Utah. I've showed you pictures of Bryce Canyon's pinnacles before. This is actually how they form. There's my obligatory national park sign of Bryce Canyon National Park. So the pinnacles that you see are created by the intersection of rivers and fractures. So fractures, this particular park, just to go back to a sec, you can see all the snow here. This park is at over 6,000 feet of elevation above sea level. For comparison, Rochester, if you live in that area, has an elevation of about 200 or 250 feet. So it is appreciably higher. It gets much colder in the winter, and snow will stick around for a lot longer. This picture was taken in April, which, as any good New Yorker knows, we could absolutely have this much or more snow in April. However, so here we have streams that flow down the side of the canyon, and streams, what they tend to do is when there's more and more precipitation, it's called headwardly erode. They kind of extend backwards until, in this case, they would intersect with one of these fractures that's widened by the freezing of water. So what that ends up doing is creating these things that kind of look sort of similar to the fins that we just saw in Arches National Park. So the streams would cut the sides back of these pinnacles, and then the fractures that you see here are the same fractures that exist in this diagram right here. So freezing and thawing of water along these fractures will eventually widen this crack, and you start to have the separation of these long, narrow features into separate pinnacles where one is separated from another. So the frost wedging that we just talked about will create the separation between the pinnacles, which are then subsequently eroded away and often fall. Good stuff. All right, so that's how the pinnacles of Bryce Canyon National Park in Utah are formed as a result of frost wedging and stream erosion. And you can see that illustrated really nicely here in these pictures where the streams cut back into the canyon here. And you can see the pinnacles lined up like little soldiers. You can see that there's new pinnacles that are beginning to become eroded and exposed along the back of the canyon. And you can see that there's like a fin of pinnacles that are about to be dissected or bisected, I guess, into these individual pinnacles. Very cool. Beautiful. Okay, so another type of weathering that can occur can impact plutons. So here we see a diagram of a pluton, and if you remember from Unit 1, we would call this a batholith, right? Because it is a giant blob of magma that cooled inside the Earth. So when things cool inside the Earth, all of the material that is overlying exerts a pressure on it. But eventually, all of this material can get eroded away, and that's when we can see granite, for example, which is most batholiths are composed of granite, exposed at the surface of the Earth. And when that happens, that downward force is removed, but the upward force that kind of keeps everything from collapsing downward, that upward force results in the expansion and the creation of what are called sheet joints in the batholith. And this is a process called exfoliation. It predominantly occurs in granite. It can occur in other rocks, but it is most common in granite when batholiths get exposed. So exfoliation of your skin, right, means to like slough off some of those dead skin cells. You can kind of think of exfoliation as like layers of an onion peeling off. These are called sheet joints. It's also sometimes called unloading because all of the material on the top got removed. And so you have the exposure of that material at the surface. But your textbook calls it exfoliation. Lots of other books call it unloading. And it creates these sheet joints where you can just kind of peel like layers of an onion, some of these layers of granite that are exposed at the surface. This one is in Acadia National Park, and you can see the, whoops, just kidding. You can see the layers of granite that are just sheeting off or exfoliating off of this batholith. So I'm going to show you this video. This comes from Yosemite National Park, and there's a big dam called Hetch Hetchy right outside of Yosemite, and there was some exfoliation that was occurring right near the dam, and so there were some geologists who were sent in, and this is really cool because you can actually see the exfoliation happen. You can see the sheet joints forming here.
Ho, 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 ho. Ho, ho, ho. Ho. All the way down. This whole seam now is active again. Lots of activity down below. It's still lifting. Did you see that? It just popped right up. Little piece flew into the air. Yeah, baby. Now maybe you'll be happy. Everything is flat again. All those pieces that were lifting just went back down.
So here is a small example of what's called an exfoliation dome. This is a place where you can see some of this exfoliation of sheet joints right here on this cute little blob of granite. So this is actually called Independence Rock, and I came upon this quite accidentally with Professor Bowen, who's another geologist at MCC. We were driving across Wyoming and pulled off to the side of the road and said, "What the heck is this? It's awesome. Look at those sweet, sweet sheet joints." So we climbed all over Independence Rock. We've brought students here a few times. It's actually in the old video game Oregon Trail, where perhaps some of you died from dysentery or a broken leg at some point playing, but it's actually a real spot on the Oregon Trail. Like, you can see some old ruts from wagon wheels, and Independence Rock was kind of a significant landmark on the Oregon Trail. In fact, people for well over 100 years would carve their names in this landmark sort of as they traveled across. You are not allowed to do that anymore, it turns out. This is a bit of graffiti that was made by a gentleman named Private Cudahy from the 4th Cavalry during some of the skirmishes between the U.S. government and the Native Americans who lived in Wyoming at the time. And so there are there's little graffiti on Independence Rock, starting at 1830, and I'm sure people still do it today, but you're not supposed to. But it's a National Historic Site. Actually, here is Professor Bowen climbing around on Independence Rock. And again, you can see these sheet joints, which again are created when the overlying pressure on a granite batholith, this is like a really small batholith nevertheless, but when that overlying pressure is removed and you have expansion of the batholith with the removal of the pressure and the creation of these sheet joints. And here's a little graveyard for some of the folks who died at Independence Rock. This is my daughter from several years ago, and we are climbing on the Tetons in Grand Teton National Park, also in Wyoming, and she's sitting on a little blob of granite, and she's wearing this sweet T-Rex shirt, and she definitely thought I was taking her picture, but I was using her for scale, because you can see here the exfoliation of the granite here as well. It's very cool. All right, so this is not something you will ever catch me doing, but this is depicting another mechanical weathering process called thermal expansion. And rocks generally create metals, are formed from metals. And so metals just like your rings, if you wear rings, they will expand when it gets hot and they will contract when it gets cold. And rocks will do the same. Can you hear my dog loudly flopping down? Sorry. So rocks will expand and contract also in response to temperature changes. And thermal expansion is something that certainly happens at really high elevations like you see here. It's also fairly common in the desert, and it's common in locations where you have repeated heating and cooling of rock. So, for example, in the desert where there's very little cloud coverage, a lot of deserts are very hot. Deserts can be hot or cold, but regardless, in a hot desert where it'll get up to well over 100 degrees during the day, it might get down to 30 or 40 degrees at night because there's no cloud cover to kind of insulate the atmosphere, and so you'll have a lot of cooling. So between these cycles of repeated heating and cooling, which results in more expansion and contraction, eventually this will lead to fracturing of the rocks. And what mechanical weathering really does is it increases the surface area where chemical weathering can then occur. So thermal expansion and contraction in areas where there are big daily fluctuations in temperature. The final form of mechanical weathering is really biological weathering or biological activity. And here we see a couple examples, but there are a ton, right? Every time humans will widen a road and we blast out rock, we are biologically weathering the rock. This is a picture also in Wyoming, lots of Wyoming and Utah pictures today, where this is a site where there were Native American petroglyphs, which is like rock art. And Professor Bowen and I were there too, just kind of driving around looking to see what there was to see. And we saw this cool tree that was like clinging to the side of this cliff. And you can see the root system is very firmly emplaced within the fracture. And that's because when it does rain, you can see from the picture, this is a dry environment. When it does rain, the roots are strategically placed because the water is going to rush into that fracture, and then the roots will uptake the moisture. And you can see that in this picture. You can also see it over in this picture. This is in Acadia National Park, where, again, the root systems are right along in the fractures to be able to exploit all the precipitation that comes through. And because there's no soil here, the water, for the most part, just runs right off the rock. So the tree roots have a very short period of time where they can really absorb some of that moisture. So one fun fact about me is that I hate snakes. And so when Professor Bowen and I were in this spot in Wyoming, there were all these signs about rattlesnake warnings, and she is not always very nice. So she snuck up behind me while I was hiking and kept like making like shaky noise, like as though she were a rattlesnake, which was not nice. And so as we were standing here looking at this picture, just behind this other photograph, there was a cave, and we were standing there, and there was no one around. Had no cell reception. We were really in the middle of nowhere, outside of a sort of city called Rock Springs, Wyoming. And we were looking at this cave, and I was like, what do you think lives in this cave? And she pondered it for a second. She's like, I don't know. Maybe like a mountain lion. And a silence fell over us as we realized that yes, there was most likely a mountain lion that lived in this cave. And without further ado, there were no more snake noises. We just silently ran to the car, and that mountain lion will come up later in this chapter again. All right, so those are your forms of mechanical weathering. And you can also see that here. This is in Craters of the Moon National Monument in Idaho. You can see a huge series of lava flows here. This is some lava flow. This is all basaltic. And then this is more of a Pahoehoe flow. But here in the fractures in the lava flows, you see wildflowers and plants. And you see that here and here. And again, that's the same idea where plants want to be where the water is. And this is how plants really go through their root systems. As the plants get bigger, they break down more and more of the rock, and they really start to develop the rock into soil. So this lava flow is about 2,000 years old. So you can see in dry environments how slowly soil development really occurs. All right, so chemical weathering is the breakdown of minerals at an internally structural level. So chemical weathering, whereas we said mechanical weathering was like taking a piece of paper and ripping it into pieces, chemical weathering is like taking a piece of paper and setting it on fire. At the end of the day, you have chemically a different substance at the end. And all forms of chemical weathering that we're going to talk about involve the presence of water. Water is involved in chemical reactions that break down the internal structure of minerals. And there's a really cool spot in South Dakota. This is called Badlands National Park, and it is just layer upon layer of what's called the White River Group. This is all shale, and shale is composed of clay minerals, which are the result of some chemical weathering processes that we will be talking about shortly. During the chemical weathering process, because you chemically end up with something at the end that is different than what you started with, it is actually a chemical change in composition during this process, where unstable minerals, because they are in new environments, will recrystallize or chemically react to turn into minerals that are stable under these current temperature and pressure conditions. Any minerals like quartz, for example, that might be stable under surface conditions are retained. And again, unstable minerals will undergo chemical changes to become minerals that are stable. So we're going to talk about 3 different chemical weathering processes. So the first is dissolution. Dissolution is illustrated here in this figure where you have a crystal of halite. So remember, halite has those 3 directions of cleavage, and it's a cute little cube, and it's chemically composed of 1 atom of sodium, and 1 ion of sodium and 1 ion of chloride, and they are chemically attracted to each other. This is an ionic bond where the positive and negatively charged ions are attracted to one another, and they form kind of a weak bond. So when salt dissolves in water, what really is happening is the sodium ion here, which is positively charged, gets surrounded pretty much on all sides by negatively charged oxygen atoms. And conversely, the chloride ion, which is negatively charged, gets surrounded by positively charged hydrogen atoms. So basically they can't really sort of rebond because they physically can't get close to one another. So dissolution is definitely something that impacts halite or rock salt, but it is also something that results in the formation of caves. So this is a picture from Mammoth Cave National Park in Kentucky, which is the longest system of caves in the world. And caves are created by groundwater that move through limestone. Limestone is composed of the mineral calcite, which you remember from your minerals lab is the mineral that will dissolve in acid. And so it might be weird to think of the fact that precipitation from the sky is acidic, but it is. It's very mildly acidic, and one of the acids in acid rain is called carbonic acid. So there's very small amounts of carbonic acid in water. It develops quite naturally. And so what I did here was give you a chemical formula that explains how carbonic acid forms, but I also put the words underneath so that you don't necessarily have to know any chemistry at all to be able to follow along. So carbonic acid is naturally formed in the atmosphere when carbon dioxide, which is CO2, will react with water vapor up in the atmosphere to combine to produce a molecule called carbonic acid, chemical formula of which is H2CO3. So then, when this very mild acid falls to Earth, it infiltrates into the ground and it becomes part of the groundwater system. When that groundwater moves through limestone, it will dissolve some of the calcite in limestone, which will create caves. We'll talk about this a lot more when we get to our chapter on caves and groundwater. Okay, so here is a picture from Capitol Reef National Park, and one of the most striking features of Capitol Reef National Park is actually just how red the rocks are in this photograph. Rocks become red through a process called oxidation, which is a chemical weathering process that impacts rocks. It also impacts like barrels like you see here, or impacts your car when it rusts. Oxidation is a process where water chemically reacts with metals, and it creates new metals that have different properties basically than what you started off with. So if you think about a rust spot on a car, it doesn't feel the same as an unrusted bit of your car, and that's because it's not the same. It's chemically a different metal. And so after this chemical reaction, different ions are carried away by the water, and it is chemically, again, something different. And the third type of chemical weathering process that also involves water is called hydrolysis. Hydrolysis is a process basically by which water will react with different minerals, typically to produce clay particles. So clay particles you can think of as like mud, and then also some ions as well. So here are some kids actually playing in mud, and they just look so happy to be so incredibly gross that I thought I would put it in. So very often water is reacting with orthoclays, and if you look, the word clay is like really, it's right in here. Orthoclays and plagioclays are the two minerals that are most directly impacted by hydrolysis. Water will react with a mineral, again, typically orthoclays and or plagioclays, and create clay. Then clay is a very common mineral that is found in sedimentary rocks. So those are your 4 mechanical weathering processes and 3 chemical weathering processes. What you're going to do next is you are going to just complete a matching assignment where you kind of review all the stuff that we just talked about, because let's face it, it's been a lot. All right, thanks for sticking with me through this. Talk to you soon.